Yes, we can go over that for sure. Sorry, Justin, I think I saw that you logged in early while I was still in block 6, and then I ended the meeting, and so that's probably how you got kicked out. Sorry about that. Yeah, I didn't mark you as absent because I knew. Yes, we can go over that. Oh, sorry. I knew you'd be back, hopefully. So here we go. Horizontal or oblique asymptotes. Is there a specific problem where you want to see that, or do we want to just pick any problem and go from there? So we can do either or. Number 9. Okay. So why don't we just go ahead and do the whole problem, so that way, in case there's questions about any other parts of it, then we got it covered. So we start with factoring, so we can see if there's anything that we need to cancel out and turn into a whole. So this is going to become x plus 3 and x minus 1, all divided by x minus 1. So I can see already this is an interesting problem, because what's going to happen is I'm going to cancel out x minus 1, and that means we have a whole, but what does that leave me with? It leaves me with just x plus 3. So it's no longer a rational function. X plus 3 is a line. So what this problem actually is a line with a hole in it. So if there's just a line with a hole in it, that means that we're not going to have any asymptotes. We're not going to have any vertical or horizontal asymptotes, because those are the things that make our rational functions. This is just a line, so it's just a straight line but with one hole in it. So let's go ahead and go through and find all the different parts to it, but just kind of keeping in mind that that's all there is to this, is just a line with a hole in it. So the hole, we can find where that hole is. I'm just going to take x minus 1, set that to 0 since that's what I canceled. So x is equal to 1, and then we plug that into the equation of the line, or the simplified part there. So I can plug in 1, so that means y is equal to 4. So we have a hole at 1, 4. And then the equation of the vertical asymptote, that normally comes from the denominator part, which there is, I mean, your denominator is 1. So it's not like you can set that equal to 0 and make it valid. It's not going to be a valid equation. So we just know that there is none. There's no vertical asymptote. Also, again, it's a line with the hole in it, so there's no way for there to be a vertical asymptote in that line. There could be zeros, since technically x plus 3 is your numerator. All you have to do is set that equal to 0, which gives us -3. So that line that we're talking about is going to cross the x-axis at x equal to -3. And it could have the y-intercept. All we have to do is plug in 0 for x. And so y is equal to 3. And then we can write both of those as points. So this would be 0, 3, and this would be -3, 0. So there's the intercepts. For the horizontal or oblique asymptote, technically this is a top-heavy function, because even when you cancel out the whole, you're left with x plus 3 divided by 1, where you have the highest degree up top because x is a degree of 1 up here, whereas down here it's x to the 0 power technically. So it's still top heavy, which would technically mean it's a slant asymptote, but because this is a line, right, there is no way of there to be a slant asymptote. Otherwise, the slant asymptote could possibly be the line, but then you would have no function, right? That doesn't make sense. So in this case, we have no horizontal or oblique asymptote. And it goes back to the same fact here because we ended up with a line. It's no longer a rational function because the denominator is just 1. Okay. Questions on that? I know that's kind of weird. A weird problem there. Okay. Do we want to see any other problems from the homework?
Could you do the one under it?
Sure.
We didn't, right?
What was that?
We didn't have to graph these, right?
No, you didn't have to graph it.
Yeah. And then the domain and range, we didn't do that either.
Yeah, so let's look at number 10. So again, we're just going to go through, factor this. So we're going to have x plus 4 and x minus 3 at the bottom. So it's similar, but not the same. X minus 3, they're both going to cancel. So it does kind of eliminate that numerator, but it's still a rational function because it's still a fraction. So that's the difference between number 9 and number 10. Number 9, the 1 was in the denominator. So it made it so it's no longer technically a rational function. It's just a line. Whereas here, the 1 is in the numerator. So it's still a fraction. X plus 4 is still creating a vertical asymptote. So this is still a rational function. We're going to just keep going and keep finding everything that we need to. The whole is going to be when I take x minus 3 and set that equal to 0, since that's what I canceled. So x is 3, and then I take that x, plug it in to that simplified fraction. So we get 1/7. And my whole here, so that's going to be 3 and 1/7. There is going to be a vertical asymptote. All I have to do is set that denominator equal to 0. So x plus 4, set that to 0. It gives me -4. So that's going to be, oops, my vertical asymptote. And then for the zeros, our numerator, we would normally set equal to 0, but our numerator is 1. So that means there is no 0. There's no 0, but there still could be a y-intercept. I'm just going to plug 0 into that simplified function again, like that. And so we get 1/4 is our y-intercept. And I can write that as 0, 1/4. Lastly, determining if there's a horizontal or oblique asymptote. So we got to do our tests, right? The 3 tests. Is it top heavy, bottom heavy, or same degree? Either way, if we look at the simplified or if we look at the original, it's a bottom heavy function. Right, the original here, without simplification, x to the first is in the numerator, x squared is the denominator, so x squared is the higher degree, so it's bottom heavy. Same thing here, technically it's x to the 0 power in the numerator and then x to the first power in the denominator. So it's a bottom heavy function. And whenever it's bottom heavy, it's automatically just y equal to 0. So those are my favorites when it's bottom heavy because it's just easy. I just know y equal to 0. It's a horizontal, just horizontal asymptote. Okay. Are there any questions on that? So for 9, the graph is just a, it's a line, right? So x plus 3 is what we're left with when we simplify. X plus 3 divided by 1. And so if you were to do division, right, x plus 3 divided by 1 is just x plus 3. So there is no horizontal or oblique asymptote because this is just a line with a hole in it. And we're going to start looking at how to graph everything. So I think that it might also help to piece everything together when we do that. Yes, we can go over number 12. So you can use either one, but when it is top heavy is when I would refer to the simplified one, because that is when you might have that possibility where it could end up being a line with a hole in it. Because if it's top heavy, then that means that you could end up with the 1 in the denominator, making it just a line. Okay. I'm going to jump over to number 12 here. So 12, again, we're going to factor from here. So that just becomes a whole lot of x plus 1s in the numerator. And the denominator is the difference of 2 squares. So it's x plus 1 times x minus 1. And what we want to do is find the whole. So I'm going to cancel out just one of those x plus 1s. And that'll leave me with x plus 1 times x plus 1 over x minus 1. And my whole, I just set this to 0. I get x is -1. And then I plug -1 into this equation. I'm just going to square that since it's the same thing. And then divided by -1 minus 1. That's just going to give me 0 over -2. 0 divided by anything is going to equal 0. So I know that the whole will be at -1, 0. And the vertical asymptote will come from the denominator. So x minus 1 set to 0 will give me x equal to +1. That is the vertical asymptote. The zeros, I'm going to set the numerator equal to 0, x plus 1. So I know it's going to happen at x equal to -1, but it's going to have a multiplicity of 2 because we have x plus 1 twice. So it's going to equal -1 with a multiplicity of 2. We're going to see an example of what the multiplicity does to the function. It does the same thing it did with polynomials. So we'll kind of see that kind of come full circle when we get there. The y-intercept, we'll just plug 0 in to the function. So again, I'm plugging into this function. I'm just squaring it up top because it's x plus 1 times x plus 1. I dropped my stylus. Hang on a sec. Okay. And what is that going to give us? 1 divided by negative 1. So y is equal to negative 1 is that y-intercept. Okay. So here's where we go to horizontal and oblique asymptotes. If we look at the simplified function, we see there's 2 terms there that are being multiplied. So when we multiply those together, our highest degree will be x squared. Our highest degree at the bottom is x to the first power, so it is a top-heavy function. In the beginning, we can also see when I multiply that, we get x cubed. And then in the bottom, it's x squared, so it's a top-heavy function. But once we cancel out the whole and we have the simplified one, and we still have a fraction, we see that it's not a line, it's still a rational function. So it is going to have a oblique asymptote because it is top-heavy. So that is the difference between this problem and number 9. Number 9, when we simplified it, it's still just a line here with a hole in it. So it can't have any asymptotes because it's a line. Over here, when we simplify it, it's still a rational function. It's still a fraction. So we can still do that division and find out where that asymptote would be. So in order to do that, I will use synthetic division, but before I can do synthetic division, I have to distribute all the way through. So this will become x squared plus 2x plus 1 divided by x minus 1. And then I'll go ahead and do synthetic division with that. So I'm going to have a positive 1 in the corner, and then 1, 2, 1 there. And synthetic division give me x plus 1. So y equal to x plus 1 is my oblique asymptote in this case. Remember, the remainder doesn't matter. Especially in this case, the remainder was 0, so it really doesn't matter. Okay. Any questions on that? Clarifications that you'd like for me to make?
Miss Martin.
Yeah.
Audric texted me that he was in the waiting room, but I don't know if he's on the right link.
Oh, sorry, he is. Let me admit him. I didn't see it come in. He should be in now. Sorry, Audric. Okay. Actually, let me make sure I have him as present. Okay, cool. So let's, if there's any other questions, let me know. Otherwise, we will jump into the notes that we've been seeing in the video series. We're gonna start to close it up with graphing today. So here we go. Let me clear this and clear that and that. Okay. So I'm going to first just kind of talk about the steps that we're going to take when it comes to graphing. And then we'll do some examples. Sorry, hang on 1 second. I need to do this attendance. Justin is here. Tong isn't here. Okay. Yeah, so these are the same notes that have been posted for a while because they're the same notes that I've been going through in the videos. So it's all of this that you've already seen in the videos on Play Pause It. So these are the same notes there. They're probably on the class schedule or posted on Schoology or both. And we've gone through all of that. Now we're talking about the graphs. So the first thing that you're going to be doing when you graph these functions is you're going to start out with what we call the discontinuities. So these are the parts of the function that are what make it a rational function. It's what breaks up our graph so that it's no longer just a polynomial or a line that we're used to, but we get these kind of pieces that are separate from each other. So the first discontinuity is the whole. And we see right there the whole, we draw the whole just like an open circle. And a hole is where a point is. So instead of just drawing a point, we draw an open circle there. All right, so whatever you find for your hole, you're going to graph it there. And then comes the vertical asymptote. So in this case, for example, A, our vertical asymptote was x equal to 3. So we see it drawn as that dashed line right on 3 on the x-axis. And then lastly, we have the horizontal or oblique asymptote. And in this case, the horizontal asymptote is y equal to 2. So we have that horizontal line right across. So those are the 3 things that we call the discontinuities. And there's specific kinds of discontinuities that we could have. The first one is a removable discontinuity. So a removable discontinuity, an example of it would be a hole. It's actually our only example of a removable discontinuity. And the reason it's called removable is because we can actually locate where the hole is at, and you can write in the coordinate of a point there, and then it's automatically filled, right? So if you have this rational function and you know that the hole is at -2 8/5, I can say, let's plot the point -2 8/5. Then I can go in, plot the point, and now all of a sudden my graph is continuous. It's no longer discontinuous. So that's why we call it a removable discontinuity, because we can actually figure out the location of that hole and fill it in if we need to. Now, our 2 asymptotes that we have, those are called non-removable discontinuities. And the reason those are called non-removable is because you can't locate where the 2 ends would come back together. For example, here, we can see that this graph is going to keep going and going and going and going infinitely downwards, whereas this part of the graph is going to keep going up and up and up and up, continuously or infinitely upwards. if I were to remove this asymptote, I have no idea where those two graphs would possibly meet, right? Maybe they would just like come together here, maybe come together somewhere up here, somewhere down here. We have no idea. There's actually no way to figure that out. So that is why we call it a non-removable discontinuity, because we can't locate a closure for the graph. Same thing with this horizontal asymptote. The graph is going off this way, the graph is going off that way. There's no way, if we remove that asymptote, there's no way that we can just easily see, oh, this is where the graph should meet, right? Whereas with the whole, yes, we can do that. We can see, oh, there's where we can fill it in, and then it's all of a sudden continuous. So that is a difference between removable and non-removable discontinuities. But those are all just, in general, discontinuities because it's breaking up our graph. So a line like this or a polynomial like that, those are all continuous. There's no break in the graph. So that's fine, right? But with a rational function, it's a discontinuous function. So we have to be able to find where those discontinuities are. And that's what we've been doing so far, is finding that. Once you find those discontinuities, there's two other things that we've been solving for. And one of those is the zeros. So we can see here the zero of our function is x equal to 2. And then we also had a y-intercept, what was that y-intercept? Let me scroll back up really quickly. Y-intercept was 4/3. So this point here, we know it to be 4/3. Once we plot those points, the intercepts, the y-intercept and the x-intercept, we can use that together with the discontinuities to use as a framework for our graph. So what I can see is these asymptotes kind of create these 4 different quadrants. See how we have a quadrant here, here, and here. We want to figure out what 2 quadrants our graph is going to be in. So a rational function is always going to exist diagonally across from each other, each of the pieces. So if I see here that I have a hole here, I have a y-intercept here and a 0 here, then I know that my graph is going to exist in this quadrant, in this section here. All I have to do is connect those points and then follow the asymptote. I know that this asymptote is going to keep going down, so my graph is going to just keep going down, never touch that asymptote. Same thing over here. I know that this horizontal asymptote is going to keep going to the left, so then my function is also going to have to keep going to the left, just never crossing that asymptote. So we found one piece here of our function. And what we're going to do for the next piece, normally what some people will have you do is plot points, right? Plug in x is equal to 4, x is equal to 5, x is equal to 6, and then get the y values. I'm not necessarily testing you on that. I know that you can plug in values and get an output and graph it. You've done that for me already. What I care about most is, can you find the asymptotes? Can you find those intercepts and the whole, and then create a rough sketch from that? That's what I most care about. So at this point, you're just going to do a rough sketch of what you see on this side, and just try and create symmetry diagonally across from it. That's all you're going to do. So see the distance, that kind of, if there's like this much of a distance, then you want to have that much of a distance that way. and then just kind of draw a graph that kind of seems similar. Okay. Don't want to overcomplicate it, because I mean, you could get exact, you could plug in numbers so you can know exactly how far out this value would be and so forth, but we're not too worried about that. We're just doing a rough sketch here. So that's all that I need you to do, is just a little rough estimate of what that would look like. You're using the stuff that you do know for sure as a framework, and so that way you know that your sketch is close to accurate, right? You're in the ballpark area. It's not something that you've totally just gotten from thin air, but it's also not an exact graph. Any questions on that? You know, that was kind of a lot of information thrown at you just now. Remember that I am posting this on YouTube, so if you want to go back and rewatch this, then I would suggest that you do that to make sure you got all the information. But we're going to do an example here together with the next 10 minutes that we have of class left. We've already done all the hard work of finding the holes and the asymptotes, so we're just going to graph here. I'm going to label really quickly, we're just going to go by one. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, -1, -2, 3, -4, -5. Just doing that all the way through. Okay. And we have our hole at 5 1/8. So I'll start with that. 5 1/8. Ooh, 1/8, I'm going to have to do a really rough estimate here and say that it's right about there. Okay, so there's 5 1/8. There's my hole. So that is check, done. Then we have a vertical asymptote at x equal to -3. So at -3, we're just going to do vertical asymptote. Check, that is done. There is no zeros. Okay, so that's taken care of. And then we have a y-intercept at 0, 1/3. Another fraction. So again, I'm going to do a little rough estimate. Let's say that is 1/3. Right there. Okay. So clearly this is not fully drawn to scale, but that's fine. We get the idea. So there's 0, 1/3. And then we have a horizontal asymptote at y equal to 0. So that's going to be right on the x-axis there. Okay. So that's all the information that we're ever going to find. In this case, the 0, there was none, so we can't put that in. But we have enough to be able to do our sketch. If we can see here, these are the asymptotes. So it's created kind of this quadrant here, another one there, and another one there. And I see that this intercept and the hole are on this side. So I can connect that, and then I know that's just going to keep going after that. And then after that intercept, I just know it's going to eventually kind of curve around and just keep following that asymptote. The thing about this, since we're doing a rough sketch, right, like this is not going to be 100% accurate. Like maybe it actually like gets closer and then goes further out. We're just doing a rough estimate, okay? So don't worry too much about that. Once you've got that, then we know that the opposite of this is going to be in this opposite little piece here. So I'm just going to do the best that I can to do a rough kind of estimate. I kind of just see this distance here and then try and maintain that same distance there, but then just kind of follow the asymptotes, and that's going to be our rational function there. Are there any questions on that problem? All right, we're going to go ahead and just do number 2 really quickly. How do you find the asymptotes again? Well, we found the asymptotes. We did the work of actually simplifying this and canceling out the holes. So this is a bottom heavy function, which gives us y equal to 0. So that's how you find the horizontal asymptote. And then when it comes to graphing it, y equal to 0 is going to be a line that crosses the y-axis at 0. That's kind of how you want to think about it. Same thing for vertical asymptote. You found that by setting the denominator equal to 0. And then we get x is equal to -3. So that means it's a line that's crossing the x-axis at -3. So there you see crossing at -3. Cool. So same process here. We had to factor and simplify to find the holes. The vertical asymptote comes from the denominator. Zeros come from the numerator. Y-intercept, you plug in 0 for x. This is a top-heavy function, so we had to do synthetic division to solve and get y equal to x plus 1 for our slant asymptote. And now we just plot all of this. So 1 9/4, so this is 1 9/4 is going to be just a little past 2. So right about here, there's our whole 1 9/4. And then we have a vertical asymptote at -3. 1, 2, 3. So I'll draw the vertical asymptote. And then we have a 0 at -2, and it has a multiplicity of 2. So with polynomials, the multiplicity meant that it was going to bounce off of that point rather than cross through. It means the same thing with rational functions, and we'll see when we graph it, we'll know exactly what that means. So we have those 3, the y-intercept 0 4/3. So 4/3, that's going to be right about, let's say here. And then the slant asymptote is going to be that diagonal line. So this technically, the parent function is y equal to x, right? It's a slope of 1, but it's been shifted up by 1. So I start here at 1. The way that I normally just go about graphing this is I find that intercept. So there's 1, because that's what this number is going to be. You're always going to end up with x plus 1, x minus 2, x minus 4, right? So whatever number that is, that's telling you where to start. If it was x minus 2, then you would start at -2 and so forth. But we're starting at 1, and then the slope of this line, the slope is 1. So from this point, we're going to go up 1 over 1, and this is where I'll do my next kind of dash there. And then again, up 1 over 1, up 1 over 1. And so we can also go down 1 over 1, down 1 over 1, and we get our slant asymptote there. And if it was x minus 2, this coefficient is always telling you the slope. So the slope would still be 1 in this case. The only time you would have to change the slope is if it was something like maybe 2x minus 2, right? Because this would be a different slope. It would be up 2 over 1. Or if it was 1/4 x minus 2, it'd be up 1 over 4. Okay, so that's how you graph your slant asymptotes. And then again, we're just going to connect what we see. I see this 2 points and that hole, and it's following the asymptote that way. These asymptotes are kind of making like slices instead of like 90-degree quadrants, but you still just follow the same way. So we can see right here what I was saying, the multiplicity means it's going to bounce off of that 0. That's what's happening. It just bounced off the 0 rather than going through the 0. So we have that part. And then the other little diagonal piece, right, there's one, and then the diagonal side is over here. So I'm just going to do a little rough sketch of what that would look like. Okay. So that takes care of graphing rational functions for us. So tomorrow we will go over graphing a little bit more, and then we'll go over domain and range. And I believe your homework has already been posted. No, it's not. So your homework is a quiz is. I'll post that right now, where kind of are just continuing to practice what we've been going over, a little bit of multiple choice with graphs, and then we'll review a little tomorrow. Or sorry, not tomorrow. We don't have class tomorrow. We have class Thursday. So we have some time to kind of work on that. Yes, I did record this session. It is still recording. I'm about to end it right now. So you can always go back and rewatch this and use it while you're doing your homework and reviewing. All right. I